Today's session is about asymptote. Let's see the definition. A straight line which tends to touch the curve but never touches is called an asymptote. So for example, I have a curve and I have an asymptote out here. They never meet. They try to come closer, but they never meet. There are infinitely small distance between the curve and the line which is tending to touch the curve in this case. Now when I just take the curve out here, there's a line touching the curve at point P, which is the tangent at P. So this is how I understand the difference between a tangent and an asymptote. A tangent touches the curve at the point and it is said to be a tangent at that point P. But an asymptote doesn't touch the curve, but it tries to come closer and closer as it proceeds further. So mathematically they meet at infinity, and as the line and curve proceed further they get closer and closer, and that is called asymptotic behavior. Now there are three types of asymptotes which you're going to learn in today's session. One is the vertical asymptote, next the horizontal asymptote, and the oblique asymptote. So let's start with vertical asymptote. How do we define the vertical asymptote? Algebraically, I define the vertical asymptote as the value of x, the real value of x for which the function or the curve y is equal to f of x is not defined. For example, I take the function y is equal to 1 by x minus 2. We all know that since the denominator is x minus 2, this function is not defined for the value x equal to 2. Therefore, this value of x equal to 2 acts as the vertical asymptote for the function y equal to 1 by x minus 2. So when we find the vertical asymptote, we take into consideration those values of x for which the whole function is not defined, in this case being x equal to 2. Let's consider the second example. Now I have the function here f from x to x plus 1 by x squared minus 5x plus 6. Now in this function the domain is x and the range is x plus 1 by x squared minus 5x plus 6. This is a rational function as it is denoted in the form of a polynomial in the numerator by the polynomial function in the denominator. So it is a rational function. Now let's see what would be the vertical asymptote for this example 2, the function in the example 2. Now when I want to identify the value of x for which this function is not defined, I clearly understand that this function would not be defined when the denominator is 0. Therefore I consider the denominator, which is x squared minus 5x plus 6, and I equate it to 0. This being a quadratic function, I can factorize this into two different linear factors as x minus 2 into x minus 3 equal to 0 by using the factorization concept. So when I just split the factors, I get the values as x equal to 2, 3. Now these are the values of x for which the function is not defined. Therefore, revisiting the definition of vertical asymptote, my vertical asymptotes would be x